Welcome to the deep dive. Today we're talking about those invisible forces, the ones that build up right beneath our feet silently, and then boom, unimaginable power unleashed.
That's right. Landscapes reshaped, lives impacted. It's quite
Yeah.
something.
So we're diving deep into earthquakes. We've gathered a whole lot of information, and our goal today is really to give you, our listeners, a clear picture of these incredible natural events.
Yeah, they're a pretty stark reminder of the dynamic planet we're on, aren't they? Sometimes just tiny tremors, barely noticeable.
Right.
Other times, absolute catastrophes that rewrite history. Understanding them isn't just academic curiosity. It's about navigating the world.
Absolutely. So our mission, if you will, is to untack the essentials. What is an earthquake, really? Why do they happen where they do? How do we even measure that immense energy?
And the effects, of course. The impacts on the planet, on us, even on our cultures over time.
We want to pull out those key insights, those sort of aha moments, so you walk away with a solid grasp of it all.
We'll try to cut through the complexity, get to the crucial stuff, the knowledge that hopefully sticks.
Okay, before we kick things off, just a quick word about who makes these deep dives possible. Today's exploration is brought to you by Stonefly. And, in a world where the unexpected, like an earthquake, can just happen, having really robust, reliable systems for your information, well, it's essential.
Absolutely crucial.
Stonefly provides innovative solutions designed for exactly that, helping you maintain resilience no matter what comes your way. We might touch on that connection again later, the whole unpredictability thing.
Sounds good.
Okay, let's unpack this. Fundamentally, what is an earthquake?
Okay, simplest terms. It's the shaking of the Earth's surface. That shaking happens because there's a sudden release of energy that's been stored up in the Earth's lithosphere.
The lithosphere, that's the rigid outer part, crust in the very top of the mantle.
Exactly. That stored energy gets released, travels outwards as vibrations. And those vibrations, those are seismic waves.
Gotcha. So we hear different words, quake, tremor, temblor. Are they basically synonyms?
Pretty much, yeah. Quake, temblor, they just mean earthquake. Now, tremor, sometimes that means a weaker quake, but it can also be used for other kinds of rumbling, maybe from volcanoes, stuff not directly from a fault breaking.
Okay.
But broadly speaking, yeah, an earthquake is any seismic event, natural or even human caused, like from mining or, fracking, that generates those seismic waves.
And where does it actually start? We always hear about the epicenter on the news.
Right. So the spot where the rock first breaks, deep underground, that's the hypocenter. Sometimes called the focus.
Hypocenter, okay.
Then imagine drawing a line straight up from that point to the Earth's surface. That spot on the surface, that's the epicenter.
Ah, okay. So the quake starts below, the epicenter is the map location directly above it. Makes sense.
Precisely.
And the main reason for this sudden break, this energy release?
The primary driver for most earthquakes, it's the rupture of geological faults. Think of them as cracks or zones of cracks between big blocks of rock.
Okay.
But other things can trigger them too. Big volcanic eruptions, sometimes even massive landslides can set off quakes.
Right.
And when we talk about seismic activity in an area, we just mean, how often they happen, what type, how big they are over time. Seismicity is kind of the average rate of shaking, the energy release in a particular spot.
Okay, so faults are key. Where do these ruptures usually happen and why there?
Well, most tectonic earthquakes, the ones tied to the big crustal plates moving, happen where there's a huge amount of stored elastic strain energy. That's the energy that forces the rock to eventually break along that fault plane.
Elastic strain, like stretching a rubber band?
Sort of, yeah. Imagine two really rough surfaces trying to slide past each other. If they have bumps or irregularities, geologists call them asperities, they get stuck, they lock up.
Okay.
This leads to what we call stick slide behavior. The plates keep trying to move, slowly but surely, right? So stress builds up around those locked bits, storing more and more strain energy, like winding a spring tighter and tighter.
Until it just snaps.
Exactly. Until the stress finally overcomes the strength of those bumps, they break, and the fault suddenly slips.
Whoosh! And that releases all the stored energy.
Right. As seismic waves, the shaking, but also as heat from the friction and energy used to actually crack the rock. This whole cycle, gradual stress buildup, sudden release, that's the elastic rebound theory.
Okay.
And what's kind of amazing is that only a small fraction, maybe 10% or even less, of the total energy released actually goes into the shaking we feel.
Wow, really? So most of it isn't even the ground shaking. That's surprising.
Yeah, most goes into breaking the rock or just turns into heat right there on the fault.
Okay, so there are different kinds of faults, right? Can you break down the main types for us?
Sure. There are three main categories related to plate tectonics: normal faults, reverse faults, which includes a type called thrust faults, and strike-slip faults.
Okay.
Normal and reverse faults involve mainly vertical movement, one block moving up or down relative to the other. Strike-slip is mostly horizontal sliding, though many quakes are actually a mix.
Let's start with normal faults. What's their deal?
Normal faults usually happen where the crust is being stretched or pulled apart, crustal extension. Think divergent boundaries where plates move away from each other.
Like Iceland, mid-Atlantic ridge sort of thing.
Exactly. Earthquakes on these tend to be, well, generally less powerful, usually below magnitude 7. The crust is often thinner there.
Okay. And reverse faults, you said those can be linked to the really big ones.
Yes. Reverse faults are where the crust is being squeezed or compressed, crustal shortening, convergent boundaries where plates collide.
Right.
And these are definitely associated with the most powerful earthquakes. We call them megathrust earthquakes. Almost all quakes, magnitude 8 or bigger, happen on these.
Wow.
Megathrusts account for something like 90% of the total seismic moment. That's a measure of the earthquake's overall size released worldwide. Thrust faults are just a specific type of reverse fault where the angle of the fault plane is relatively shallow.
90%. That's huge. Okay, and the third type, strike-slip.
Strike-slip faults are where the two sides slide horizontally past each other. The classic example is a transform boundary, like the San Andreas Fault in California.
Right, everyone knows that one.
These faults are typically almost vertical. They can still produce major earthquakes up to around magnitude 8 or so. But because they're vertical, the rupture area within the brittle part of the crust is usually more limited compared to those wide, shallow-dipping reverse faults in subduction zones. So truly giant magnitudes, like 9 plus has, are less likely.
That difference in potential size based on fault type, that's a really key point. You mentioned stress levels earlier, too. How do they relate?
Yeah, there's a kind of hierarchy. Thrust faults generally need the highest stress levels to rupture. Strike-slip faults are intermediate, and normal faults need the lowest stress levels.
Why is that?
It relates to the direction of the main pushing force, the principal stress. For normal faults, gravity pulling down is basically the main stress. For thrust faults, the rock wants to escape upwards, so the weight from above is actually the least important stress. Strike-slip is somewhere in between, okay? And this difference in the stress environment can affect how much the stress drops during the quake, which influences how much energy gets radiated as seismic waves.
And the length of the rupture, how far along the fault does it actually break?
Oh, the maximum lengths can be absolutely mind-boggling. In subduction zones, think Alaska 1957, Chile 1960, Sumatra 2004, the ruptures can stretch for about 1,000 kilometers.
1,000 kilometers? It's hard to even picture.
It really is.
Right.
On strike-slip faults, like the San Andreas or the North Anatolian in Turkey, the longest ruptures are more like half to maybe a third of that. Normal faults tend to have even shorter maximum lengths. It's just immense scales we're talking about.
Absolutely. Okay, let's talk energy. Magnitude scales are logarithmic, right? What does that actually mean in terms of power unleashed?
Right, logarithmic. It means for every whole number increase in magnitude, the energy released goes up by about 30 times. Roughly 32 times, actually.
30 times. So a magnitude 6 is 30 times more energy than a 5.
Exactly. And a magnitude 7 is about 30 times that. So almost 1,000 times more energy than a 5.
Wow.
To give you a scale, an 8.6 magnitude quake releases about the same energy as, wait for it, 10,000 World War II era atomic bombs.
10,000. That's almost impossible to comprehend.
It's truly an exponential jump in power.
And you said this energy release is tied to the area that ruptures.
Yes. The energy, and so the magnitude, is proportional to the area of the fault that slips and how much the stress drops, the stress drop. Bigger rupture area, bigger stress drop generally means a bigger quake.
Okay.
But the really critical factor limiting the maximum possible magnitude isn't always the fault's length. It's the width of the fault plane that can rupture. And that width can vary hugely, like by a factor of 20 or more.
How so?
At converging plate boundaries, those subduction zones, the fault plane often dips at a really shallow angle, maybe only 10 degrees or so.
Okay.
That shallow angle creates a massive contact area between the plates, sometimes 50 to 100 kilometers wide.
Okay.
Think about the 2011 Japan quake or the 1964 Alaska quake.
Right. Huge events.
It's that enormous rupture area allowed by the shallow dip that makes those truly colossal magnitude 9+ earthquakes possible.
So that shallow angle is key for the monster quakes.
That way.
Got it. What about depth? We hear about shallow versus deep earthquakes.
Right, the depth of the focus, the hypocenter, varies quite a bit. Most tectonic quakes, especially around the Pacific Ring of Fire, are pretty shallow, less than 70 kilometers deep.
Okay, those are the most common.
By far. Then you have mid-focus or intermediate depth quakes, between 70 and 300 kilometers down. And then in subduction zones where one plate dives deep under another, you can get deep focus earthquakes. These can happen way down, from 300 to even 700 kilometers deep.
700 kilometers? That's incredibly deep. How can rock even break like that down there? Isn't it too hot and squishy?
That's the puzzle. It should be too hot and under too much pressure to fracture like brittle rock near the surface. It should deform, flow more like putty.
So what's the theory?
One leading idea involves a mineral called olivine, which is common in the mantle rock being subducted. Under intense pressure deep down, olivine can suddenly transform into a denser crystal structure called spinel.
A phase transition.
Exactly. This change takes up less space, a sudden volume decrease. And that rapid change could potentially trigger faulting, causing a deep earthquake. It's still an active area of research, though.
Fascinating. Mineral physics causing quakes deep underground. What about volcanic earthquakes? Are they the same thing?
Well, volcanoes often have earthquakes, yes, but they can be caused by two main things. Regular tectonic faults in the area or the movement of magma itself under or inside the volcano. These volcanic quakes can sometimes be an early warning sign. Like before Mount St. Helens erupted in 1980, there was a noticeable increase in earthquake activity.
Right.
And sometimes you get earthquake swarms, lots of small quakes clustered together. That can indicate where magma is moving beneath the surface. Scientists use seismometers and ground deformation monitors to track these swarms and help forecast eruptions.
So like the earth clearing its throat. Okay, let's talk about the actual rupture process. How does it unfold once it starts?
It kicks off that initial slip on a small patch of the focus. Then that rupture starts to spread out along the fault surface, kind of like a crack spreading in glass.
Okay.
It keeps going laterally until it hits some kind of barrier, maybe the end of that fault segment, or an area where the stress just isn't high enough to keep it going.
And how deep can it go?
Well, for bigger quakes, the depth is limited downwards by that zone where rocks get too ductile, too flowy, and upwards by, well, the Earth's surface.
Right.
The really fine details of how that rupture zips along are still tough to study. It happens so fast under such extreme conditions, hard to replicate in a lab, and hard to record super close up because the shaking is just too intense.
I've heard about some quakes that break the speed limit, so to speak. Super shear earthquakes.
Yes. Super shear ruptures, they actually propagate faster than the S waves. The shear waves travel through the rock around them.
Faster than their own shear waves?
I know. It's wild. Seems to happen mainly in large strike-slip earthquakes. The damage from the 2001 Kowloon quake in China was unusually widespread, and that's been linked to a sort of sonic boom effect from the super shear rupture.
A sonic boom from the fault breaking.
Kinda, yeah. And parts of the big Turkey Syria quakes in 2023 also involved super shear rupture. It's like the fault is literally outrunning some of the shaking it's creating.
Incredible. What about the opposite? Slow earthquakes. Sounds contradictory.
It does, doesn't it? But slow earthquakes involve fault ruptures that travel much, much slower than normal. A really dangerous type is the tsunami earthquake.
Why dangerous?
Because the rupture is so slow, the ground shaking felt on the coast might be relatively weak. People might not realize a huge tsunami is on its way because they didn't feel violent shaking.
Oh, wow. That's terrifying.
It is. The 1896 Sanrico earthquake in Japan was a tragic example. Weak shaking, but a massive, devastating tsunami followed.
So the lack of strong shaking can be dangerously deceptive. You also mentioned pressure changes, fluids in the rock.
Yes. During the rupture, friction generates a lot of heat right on the fault plane. This heat can dramatically increase the pressure of fluids, mostly water, trapped in the tiny pore spaces within the rock. It can even vaporize the water sometimes.
And that affects the slip.
It can, yeah. During the quake itself, the co-seismic phase, this high fluid pressure or overpressure, can influence how easily the fault slips and how fast it goes.
Okay. And afterwards, aftershocks.
Right. In the post-seismic phase, after the main shaking stops, this pocket of high fluid pressure can slowly spread out into the surrounding rock fractures. This increased pressure effectively lowers the friction holding faults together, kind of like lubricating them. And that can trigger aftershocks.
Ah, interesting link.
And this whole process is also relevant to induced seismicity, where injecting fluids deep underground, like for wastewater disposal or fracking, increases pore pressure and can trigger earthquakes.
That connection to human activity is definitely something to keep in mind. Okay, shifting slightly, what about external forces? Can the moon and sun's gravity tides actually trigger quakes?
It's a really interesting question.
Yeah.
And there is some evidence suggesting that, yes, tidal forces might have a subtle influence.
Subtle, but real.
It seems so. The stresses they induce are pretty small compared to the tectonic stresses building up over years. But if a fault is already right on the brink, already critically stressed and ready to go,
The tiny extra pull from the tide could be the last straw.
that's the idea. It might just be enough to nudge it over the edge and trigger the rupture. Still debated how significant it is overall, but the connection seems to be there in some cases.
Wow, even the cosmos playing a small part. Okay, earthquakes rarely happen alone, right? We hear about aftershocks, swarms. What's the difference?
That's right. Most quakes are part of a sequence, linked in space and time. Even the smaller tremors in these sequences can tell us a lot about the faults involved.
So, aftershocks first. What are they exactly?
An aftershock is simply an earthquake that follows a larger initial earthquake, which we call the main shock. They happen in the same general zone.
And they're smaller?
Usually, yes. They're basically the crust adjusting to the big stress changes caused by the main shock. The main rupture changes the stress distribution on the fault and in the surrounding rock, and the crust settles into a new equilibrium, causing these smaller adjustments.
Can they still be dangerous?
Oh, definitely. Even smaller aftershocks can cause significant damage, especially to buildings already weakened by the main shock. And sometimes, though it's less common, an aftershock can actually be larger than the initial event.
Really? What happens then?
Then seismologists reevaluate the sequence. The biggest event becomes the main shock, and the earlier one is reclassified as a foreshock.
Okay, so how are earthquake swarms different?
Swarms are also sequences of quakes in a specific area over a short time, but the key difference is there's no single clear main shock that stands out as much larger than the rest.
So just a bunch of similar-sized quakes.
Pretty much. You get a cluster of activity, but not that typical pattern of one big one followed by gradually decaying smaller ones. Yellowstone had a well-known swarm in 2004, and there was one in Southern California's Imperial Valley in 2012.
What causes swarms, usually?
Often related to the movement of fluids underground, maybe magma rising, or changes in groundwater pressure. Not always a main fault rupture driving it.
Got it. More like a sustained rumble. I've also heard the term earthquake storms. Sounds dramatic.
It is pretty dramatic. Earthquake storms are clusters of earthquakes happening along a fault, but spread out over a longer time, maybe years or even decades.
How are they linked?
Each quake in the storm can be triggered by the stress changes caused by the previous quakes in the sequence. They sort of cascade along the fault.
Like dominoes falling?
A bit like that, yeah.
Yeah.
And unlike typical aftershocks, some of the later quakes in a storm can be just as large and damaging as the earlier ones.
Any examples?
The classic example is the North Anatolian Fault in Turkey during the 20th century. There was a sequence of about a dozen major earthquakes that essentially migrated westward along the fault over decades.
Wow. So one quake sets up the conditions for the next one down the line.
Exactly. And scientists think similar storm-like patterns might have happened in the past in places like the Middle East, based on historical records. These major fault systems can have really complex long-term behavior.
Definitely seems that way. Okay, let's talk frequency. How often do earthquakes actually happen worldwide?
Globally, it's estimated there are about 500,000 earthquakes every year that are strong enough for our instruments to detect.
500,000.
Yep. Now, only about 100,000 of those are actually felt by people. Minor quakes are happening constantly, all the time, especially in active zones.
And there's a pattern to the sizes, right?
Yeah.
Lots of small ones, fewer big ones.
Absolutely. It's an exponential relationship. Far more small quakes than large ones. For every magnitude 5 quake, there are roughly 10 times as many magnitude 4s. For every magnitude 6, 10 times as many magnitude 5s, and so on.
That's the Gutenberg-Richter law.
That's the one. It describes this statistical distribution of earthquake sizes pretty well. Even somewhere relatively quiet seismically, like the UK, scientists can estimate average return periods for different magnitudes based on this idea.
So the big destructive ones are thankfully rare, but the planet is constantly adjusting on smaller scales we don't even notice.
That sums it up well.
Does it feel like there are more earthquakes now, or is that just better reporting and detection?
It mostly just seems that way. The reason we hear about more earthquakes now is overwhelmingly due to huge improvements in technology and the sheer number of seismic stations we have globally.
So we're just better at spotting them.
Exactly. We have thousands of supersensitive stations now, compared to maybe a few hundred much cruder ones a century ago. We're detecting vastly more small quakes that would have gone completely unnoticed before.
What about the big ones? Has their rate changed?
According to the U.S. Geological Survey, the long-term average since about 1900 has been pretty stable, roughly 18 major earthquakes, magnitude 7.0 to 7.9, and about one great earthquake, magnitude 8.0 or higher, per year on average.
Yeah, pretty consistent over the long haul.
Yeah. There have been some years recently with fewer major quakes, but that's likely just normal statistical fluctuation, not a sign that things are fundamentally calming down.
That's good to know. It's detection, not necessarily a surge. Where do most quakes actually happen geographically? Is it random?
Oh, definitely not random. The vast majority, something like 90% of all earthquakes, and about 81% of the very largest ones, occur in specific zones.
The Ring of Fire.
That's the main one, yeah. The Circum-Pacific Seismic Belt, the Ring of Fire. It's this massive horseshoe-shaped zone around the Pacific Ocean, about 40,000 kilometers long.
Why there?
It's where the Pacific tectonic plate interacts intensely, with all the surrounding plates colliding, sliding past, diving underneath. All that action creates enormous stress.
Okay. Anywhere else significant?
Yes, another major belt is the Alpine Himalayan belt, stretching from the Mediterranean across the Middle East and through the Himalayas into Southeast Asia. Basically, most big earthquakes happen along the boundaries where these massive tectonic plates meet.
And with more and more people living in huge cities in these risky areas.
That's a huge concern. Yeah, the rapid growth of megacities, think Tokyo, Mexico City, Istanbul, Tehran, in high-risk seismic zones, is dramatically increasing the potential for catastrophe.
A really big one hitting a major city.
Some seismologists warn it could be unprecedented. Millions of lives could potentially be lost if a massive quake struck directly beneath or very near one of these incredibly dense population centers, especially where building standards might be lacking. It's a really sobering thought.
Absolutely. We touched on induced seismicity earlier, humans causing quakes. Can we revisit that? How does it work?
Right. So while most quakes are natural, certain human activities can change the stress balance in the crust enough to trigger earthquakes. We call it induced seismicity.
What kind of activities?
Things like building massive dams and reservoirs. The weight of the water can add stress. Extracting large amounts of material like coal mining or oil and gas production. And probably the most talked about one recently is injecting fluids deep underground.
For wastewater disposal, fracking.
Both? Yeah. Injecting wastewater from oil and gas operations or fluids used in hydraulic fracturing increases the pressure in the rock pores down there.
Yeah.
As we discussed, that can effectively unclamp existing faults, making them more likely to slip.
Are these induced quakes usually big?
Most are quite small, thankfully. Magnitude 3 or 4, maybe less, often not even felt. But there have been larger, damaging ones linked to fluid injection.
Like the Oklahoma ones?
Exactly. Oklahoma saw a huge spike in seismicity, including a magnitude 5.7 quake in 2011, strongly linked to deep wastewater injection from oil production. The link between large dams and triggering major quakes is also studied, though it's often more complex to prove definitively.
It really shows how our actions can ripple through these powerful geological systems. Okay, let's switch to how we actually record and measure these things. Seismographs are the key, right?
They are. Earthquakes are recorded by networks of seismographic stations spread across regions or even the whole globe. Each station has a seismometer.
What's that too?
It's a very sensitive instrument designed to detect and precisely measure ground movement at that spot. When a quake happens, the fault slips. Energy radiates out as those seismic waves. The waves reach the station, the ground vibrates, and the seismometer records that motion over time. That recording is called a seismogram.
Like the earthquake's fingerprint.
In a way, yeah. It contains a ton of information about the quake.
So how do scientists use that data to say how big the earthquake was? There are different scales, right? Richter scale, moment magnitude.
Right. We need ways to quantify the size or strength. The most common measure is magnitude. The goal is a single number representing the quake size at its source, ideally the same no matter where you measure it. The Richter scale was famous early on, developed in the 1930s. But it has limitations, especially for very large or distant earthquakes. It tends to saturate, meaning it doesn't accurately reflect the size differences between really huge quakes.
So what's used now, mostly?
For official reporting, especially by agencies like the USGS, the moment magnitude scale, MRW, is the standard now. It gives a more physically meaningful measure of the total energy released based on the fault area that slipped, how much it slipped, and the rock rigidity. It doesn't saturate like Richter, so it works better for the biggest quakes.
But other scales might still be used sometimes.
Oh yeah, various other magnitude scales exist and are used for specific research purposes, or for comparing different types of seismic events, or maybe for very small local quakes. But moment magnitude is the main one you'll hear reported for significant events.
Got it. And magnitude is different from intensity, right? People sometimes mix those up.
Very different, yes. Crucial distinction. Magnitude. One number for the quake's size at the source, the hypocenter.
Oh.
Intensity describes the effects of the earthquake, the shaking, the damage at a specific location on the surface.
So intensity varies from place to place.
Exactly. An earthquake has only one magnitude, but it can produce many different intensity values depending on how far you are from the epicenter, the local geology underneath you. Soft soil can amplify shaking, hard rock might dampen it, building construction, etc. Intensity scales, like the modified Mercalli scale, are descriptive based on what people felt and the observed damage.
That's a really helpful distinction. Size at source versus effect at location. Now, those seismic waves you mentioned. P waves, S waves.
Right. Every quake generates different types. Broadly, you have body waves that travel through the Earth's interior and surface waves that travel along the surface.
Okay, body waves first.
Two main types.
Yeah.
P waves, P for primary, because they arrive first. They're compressional, like sound waves. The ground pushes and pulls in the same direction the wave is traveling.
Like a slinky pushing together and stretching out.
Good analogy. Then there are S waves, S for secondary. They arrive later. They're shear waves. The ground moves side to side or up and down, perpendicular to the direction the wave is traveling.
More like shaking a rope up and down.
Exactly. And P waves are always faster than S waves in the same material. Then you have surface waves, like Love waves and Rayleigh waves, which are often responsible for the most damage because they travel along the surface where we live and build.
So P waves arrive first, then S waves, then surface waves. Are S waves generally more damaging than P waves?
Generally, yes. While P waves give the first little jolt, the S waves often have larger amplitudes, and that shearing motion shaking things side to side and up and down is particularly damaging to structures. Surface waves arriving even later can cause slow, rolling motions that can also be very destructive, especially to tall buildings or long structures like bridges.
And the different arrival times tell scientists where the quake happened.
Precisely. Because we know the typical speed difference between P and S waves through the Earth's crust and mantle. P waves travel about 1.7 times faster than S waves. By measuring the time gap between the P wave arrival and the S wave arrival at several different seismic stations.
You can triangulate.
Essentially, yes. The longer the time gap, the farther away the earthquake is. With data from at least 3 stations, you can pinpoint the epicenter location. The arrival times can also help estimate the hypocenter's depth.
Is there a quick rule of thumb for distance?
There's a rough one. The distance in kilometers to the epicenter is approximately the SP arrival time difference in seconds, multiplied by about 8. It's approximate. Depends on the local geology, but gives a quick estimate.
Handy. And for a quake on the other side of the world, the very first signal to arrive would be a P wave that went deep through the Earth.
That's right. The fastest path is often deep through the mantle for distant earthquakes. Those P waves are the first messengers.
I saw mention of Flynn-Engdahl regions. What are those used for?
Ah, yes. The Flynn-Engdahl regions, or FE regions, the world is divided into 754 of them. It's basically a standardized way to geographically classify earthquake locations for global reporting and data analysis.
So everyone knows exactly which part of the world is being referred to.
Pretty much. They're based on a mix of political and geographic boundaries and also seismic activity patterns. More active areas tend to have smaller, more detailed regions. It just provides a consistent framework for seismologists worldwide.
And when an official report comes out, what's the standard info included?
Typically, you'll get the magnitude, usually moment magnitude, the exact date and time in UTC, Coordinated Universal Time, the epicenter coordinates, latitude and longitude, the hypocenter depth, the geographical region name, or FE region,
Okay.
distances to nearby cities, some measure of the uncertainty in the location and magnitude, maybe some technical details about the stations used, and a unique event ID number.
Quite comprehensive. Now, this was fascinating, measuring gravity changes to detect quakes. That's new, right?
Relatively new and very exciting, yes. It was a big realization around 2016. When a huge earthquake happens, it moves enormous amounts of rock mass very quickly. That sudden mass shift causes tiny, almost instantaneous changes in the Earth's gravitational field nearby.
Instantaneous.
Yeah.
Faster than seismic waves.
That's the key. These gravity signals, called prompt elastogravity signals, or PEGs, travel at the speed of light, much faster than even P waves. Scientists realized they could detect these subtle gravity changes using very sensitive instruments.
And they proved it worked.
Yes, they went back and analyzed data from the massive 2011 Tohoku-oki earthquake in Japan and found clear evidence of these prompt gravity signals arriving before the seismic waves at distant stations.
What's the potential application?
Faster earthquake early warning. If you can detect the gravity signal instantly, you could potentially issue alerts several seconds, maybe even tens of seconds, earlier than systems relying on detecting the P wave. Those extra seconds could be crucial. Still under development, but very promising.
Truly cutting-edge stuff. Okay, let's talk about the impacts, the effects. Often devastating. What are the main ways earthquakes cause damage?
The primary effects are the ground shaking itself and ground rupture, where the fault actually breaks the surface. The shaking damage depends heavily on the quake's magnitude, your distance from it, and crucially, the local geology.
Local geology, how does that matter?
Oh, hugely. Soft, loose soils, like in a river valley or an old lake bed, can amplify seismic waves dramatically. It's called site amplification. A quake might feel much stronger on soft soil than on solid bedrock just a short distance away. The shape of underground rock layers can also focus seismic energy in certain spots.
So where you are standing really matters. What about ground rupture?
That's the actual physical tearing or displacement of the ground along the fault trace. In a big quake, the ground might shift horizontally or vertically by several meters.
That sounds incredibly dangerous for anything built right on the fault.
It is. Dams, bridges, pipelines, buildings. If they straddle an active fault that ruptures, they can be torn apart. That's why detailed fault mapping is so critical for planning major infrastructure.
And then there's liquefaction. That sounds like the ground turning to liquid?
That's a pretty good description. It happens in specific conditions. Loose, sandy, or silty soil that's saturated with water, like near rivers or coastlines.
Okay.
The intense shaking increases the water pressure between the soil grains until the grains essentially lose contact and the soil temporarily behaves like a thick liquid, losing all its strength.
What happens then?
Buildings can tilt or sink. Underground tanks or pipes can float upwards. Roads can crack and buckle. It can cause incredible damage. The 1964 Alaska earthquake had massive liquefaction effects in Anchorage.
The human impacts are just immense, often tragic.
Absolutely devastating. Injuries, loss of life from collapsing buildings.
Yeah.
But also damage to lifelines. Roads, bridges, power, water, communication, loss of essential services, property destruction.
And the aftermath.
Risk of disease from poor sanitation, lack of clean water, shortages of food, shelter, and the long-term mental health toll, trauma, loss, displacement, is profound.
And it often hits vulnerable communities hardest.
Tragically, yes. Developing communities often have less resilient buildings, fewer resources for response and recovery. The impacts can be much more severe and last much longer.
Landslides too, right? Earthquakes can trigger those.
Definitely. Strong shaking can destabilize slopes, leading to widespread landslides, rock falls, debris flows, especially in mountainous areas.
Where is this a major hazard?
China has seen huge fatalities from earthquake-triggered landslides, like in the 2008 Sichuan quake. Peru, Pakistan too. Strike slip and thrust reverse faults in mountain belts are often associated with triggering major landslide events.
And fires. Sometimes the fires after a quake are worse than the shaking.
That can happen, yes.
Yeah.
Shaking breaks gas lines, downs power lines, creates ignition sources. At the same time, it can break water mains, leaving firefighters without water pressure to fight the blazes.
Like San Francisco in 1906.
The classic tragic example. Much of the destruction and loss of life in 1906 was due to the fires that raged for days afterwards, largely uncontrolled because the water system was crippled by the quake.
And for coastal areas, the threat of tsunamis looms after an offshore quake.
Yes. Tsunamis are giant sea waves, usually caused by a sudden displacement of the ocean floor, most often from a large earthquake under the sea, especially a subduction zone megathrust quake.
How big are we talking?
The earthquake generally needs to be magnitude 7.5 or greater to generate a really destructive tsunami. The waves travel incredibly fast across the deep ocean, like 600, 800 kilometers per hour jetliner speed.
But they get bigger near shore.
Right. As they enter shallower water, they slow down, but the wave's energy piles up, causing the wave height to increase dramatically. They can flood coastal areas with devastating force.
Can earthquakes cause other kinds of floods too, not just tsunamis?
They can. Shaking can damage dams, potentially leading to failure and downstream flooding. Also, large earthquake-triggered landslides can block rivers, forming unstable natural dams.
And if those landslide dams break,
Catastrophic flash floods downstream. Suez Lake in Tajikistan was formed by a huge quake-triggered landslide dam in 1911, and there's ongoing concern about the potential for it to breach someday.
it's just a whole cascade of potential hazards from one event. So, facing all this, how do we manage the risk? Prediction seems like the holy grail, but it's still out of reach.
True predictions specifying exact time, location, and magnitude in advance is not scientifically possible right now, despite a lot of effort. We simply don't understand the pre-rupture process well enough.
What about common myths, like earthquake weather?
Total myth. No correlation whatsoever between weather conditions and earthquake occurrence. Same for the idea that they happen more often in the early morning. Statistically not true. These are deep earth processes, largely independent of surface weather.
But we do have forecasting, right? Looking at probabilities over longer times.
Yes, forecasting is different. It's about assessing the probability of an earthquake of a certain size happening in a particular region over a period of years or decades.
How is that done?
Based on understanding past earthquake history in the area, the rate plates are moving, identifying active faults, measuring strain buildup using GPS. It allows us to say, for example, there's a certain percent chance of a magnitude 7 or larger quake on this fault segment in the next 30 years.
Which is useful for planning.
Absolutely. Crucial for building codes, infrastructure design, emergency preparedness planning, insurance rates. It's about long-term hazard assessment, not short-term prediction.
And early warning systems. They don't predict, but they give a few seconds notice.
Exactly. Earthquake early warning, EEW systems, detect a quake after it has started, near the source. They rely on detecting the faster, less damaging P wave first.
And send out an alert before the stronger S waves arrive.
Right. The system rapidly estimates the location and magnitude for the P wave, determines which areas will experience strong shaking, and sends out alerts via phones, sirens, broadcasts. The warning time depends on your distance, maybe a few seconds to maybe a minute or so.
Is that enough time to do anything?
It can be. Enough time to drop, cover, and hold on. For automated systems to slow trains, stop elevators, shut off industrial processes or gas lines, those seconds can save lives and reduce damage.
So prediction is out for now. Forecasting helps long term. Warning gives seconds. Preparedness seems key. What does that involve?
It's multifaceted. Earthquake engineering designs buildings and bridges to withstand shaking better. Seismic retrofitting strengthens older, vulnerable structures.
Okay.
Earthquake insurance helps financially. Emergency management agencies plan for response and recovery. Even AI is being used now, like expert systems to help assess building safety after a quake.
And for individuals, what can people do?
Simple things help. Secure heavy furniture, water heaters, bookshelves so they don't fall. Know how to shut off gas and water mains. Have an emergency kit and plan. Practice drop, cover, hold on. If you're near a coast, know your tsunami evacuation route. Preparedness makes a huge difference.
Crucial steps for everyone in earthquake zones. Now, culturally, earthquakes have loomed large in human history and myth, haven't they?
Oh, absolutely. For millennia, people tried to explain these terrifying events. Early Greek philosophers thought it was trapped air or imbalances of earth and water. Pliny the Elder even called them underground thunderstorms.
And myths, gods and monsters.
Loads of them. Norse mythology blamed Loki's struggles while chained underground. The Greek god Poseidon wasn't just god of the sea, but the earth shaker, causing quakes with his trident.
I've heard about the Japanese catfish.
Namazu, yes. A giant catfish living underground whose thrashing caused earthquakes. The god Kashima supposedly tried to keep it pinned down with a stone. Many cultures linked quakes to divine anger or cosmic battles. Biblical accounts also mention earthquakes at key moments.
And in modern culture, books, movies.
Popular culture is definitely shaped by memories of real disasters. Kobe 95, San Francisco 1906. Fictional quakes often strike suddenly, focusing on the immediate chaos and survival struggle.
The big one, hit in California, is a common theme.
Oh yeah. Novels like Richter 10, movies like San Andreas or 2012, they tap into that deep-seated fear. Interestingly, how people react psychologically is portrayed very differently across various films and books.
What does real research say about psychological impacts?
Disaster psychology emphasizes the importance of support systems, especially stable caregivers for children, and validating people's reactions to trauma, loss, displacement. It's normal to have strong reactions, not something to be pathologized. Resilience is key.
Fascinating how these events weave into our stories. And finally, it's not just Earth, right? other planets have quakes.
That's correct. Similar processes happen elsewhere. We've detected Mars quakes on Mars with robotic landers like InSight.
Learning about Mars' interior from its quakes.
Exactly. And the Apollo missions left seismometers on the moon that detected thousands of moonquakes, telling us about the moon's internal structure and activity. It shows these seismic processes are likely common on rocky bodies throughout the universe.
Puts our own planet's rumblings into a cosmic context. Okay, as we start to wrap up this deep dive, it's really clear just how vital understanding earthquakes is.
It truly is. They're a fundamental part of how our planet works, constantly reshaping it. And the more we understand about their causes, their effects, how they work, the better we can prepare and mitigate the risks they pose.
And speaking of mitigating risks in an unpredictable world, that brings us back neatly to our sponsor, Stonefly.
Hmm.
Just like the Earth can unleash unexpected forces, disruptions to our data, our critical systems can happen anytime. Stonefly focuses on providing solutions, products, services designed specifically to help manage, protect, and ensure the resilience of that vital information.
Which is incredibly important in today's world.
Right. Whether it's about preventing data loss, ensuring business can continue after a disruption, or just providing secure, reliable access, Stonefly offers ways to navigate uncertainty with more confidence. We really encourage listeners to check out their offerings.
Definitely. Understanding potential risks, geological or technological, is the first step towards managing them effectively.
So, a key takeaway for everyone listening. Earthquakes are these incredibly complex, powerful events. They have huge impacts, driven by deep geological processes we're constantly learning more about, trying to understand and manage better.
And maybe a final thought to leave you with. Considering the colossal energy earthquakes release, what other natural forces shape our planet so dramatically? And how do we continue to learn to live alongside these powerful, sometimes unpredictable forces?
Thank you so much for joining us on this deep dive into the often awe-inspiring, sometimes terrifying world of earthquakes. We really hope you found it insightful.
And we look forward to exploring another fascinating topic with you next time.